Usually when you look up at the night sky, there is this really profound expectation of permanence.
Yeah, absolutely.
It feels like you're looking at a beautifully painted ceiling in a grand cathedral, you
Yeah.
know? You just expect the North Star to be exactly where it's always been.
Right.
You expect the Big Dipper to keep its familiar shape. And you absolutely expect the bright, colorful stars scattered across the dark to just, keep on shining night after night the exact same way they did for our ancestors.
We really do treat the sky as this fixed backdrop to human history. Like, it's a reliable map that never changes. It provides a real sense of comfort.
It does, but when you start digging into astrophysics, you suddenly realize that that painted ceiling is actually a wildly dynamic, intensely violent theater.
Oh, very violent, yeah.
Today, we are taking you on a deep dive into an event that is going to completely shatter that illusion of permanence. We're pulling from a really fascinating stack of sources today. We've got a documentary script from the Dark Matter Files, research data from the Harvard-Smithsonian Center for Astrophysics, some stuff from Tohoku University, and actual observation logs from NASA and the James Webb Space Telescope.
It's a great collection of data, really cutting edge.
Yeah, and the mission of our conversation today is to explore a literal ticking time bomb in our cosmic backyard, a star called Betelgeuse. Because the single point of light represents the only cosmic catastrophe that you can simply step outside, stand in your driveway, and watch waiting in the dark.
Yeah, we are not just talking about a faint dot of light flickering out. We are examining a fundamental redefinition of what the sky looks like, an event that will alter the constellation Orion permanently.
So if you go outside tonight and find Orion the Hunter, look for those 3 famous stars making up his belt, and then look slightly up and to the left. You're going to see a reddish-orange, somewhat blurred, pulsing star.
That's the one.
That is Betelgeuse. It looks like a permanent fixture, but it is actually dying. And when it finally explodes, it will be the most spectacular event any human being has ever witnessed.
Okay, let's unpack this. Before we get into how the star physically breaks down, we have to talk about what kind of monster we are actually looking at. Because the word star it feels entirely inadequate.
It is entirely inadequate. Betelgeuse is classified as a very supergiant. And to understand what that means, we have to look at the mechanical balance of a star.
Okay.
For most of a star's life, it is essentially an ongoing nuclear explosion that's being contained by its own gravity.
Right, like a tug of war.
Exactly. Gravity wants to crush the star inward, while the nuclear fusion at the core creates immense outward pressure. They sit in perfect balance. But when a massive star starts running low on its primary fuel, hydrogen, gravity starts to win.
So it starts shrinking. The core does, yeah. It crushes the core, eating it up immensely, which then triggers the fusion of heavier elements. And this sudden surge in the core temperature pushes the outer layers of the star unimaginably far out into space.
And the scale of those outer layers being pushed out is what absolutely broke my brain while I was reading the documentary script. I was trying to wrap my head around just how massive this thing is. Let's imagine replacing our sun at the center of the solar system with Betelgeuse.
Okay, terrifying thought experiment.
Right, if you did that, it wouldn't just swallow the Earth. Its surface would consume Mercury, Venus, Earth, and Mars. And the edge of this star would keep going past the orbit of Jupiter.
Yeah.
We are talking about a physical diameter stretching roughly 778 million kilometers, like 1,400 times the diameter of our sun, 100,000 times brighter, and it holds up to 19 times the mass.
What's fascinating here is how that sheer physical scale translates to cosmic distance, our human perception of safety. Betelgeuse is approximately 700 light years away from Earth.
Which sounds like a lot. Like, in everyday conversational terms, 700 light years sounds like a massive buffer zone. Are we safely out of the way?
Well, in conversational terms, yes. But in the context of a supernova, that is historically uncomfortably close.
Great. Really?
Oh, yeah. To put that in perspective, the last time humanity saw a supernova with the naked eye was in 1987. That event was in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, and it was 168,000 light years away.
Wow. Okay, so 168,000 years.
Right. Betelgeuse is 240 times closer than that. When this star detonates, it will stop traffic globally. People will literally wake up in the middle of the night because their bedrooms are full of it.
Because it's swelled to that monstrous size, right? Those outer layers are just barely holding on to the star's gravity. A terrifying thing we saw it do a few years ago. Here's where it gets really interesting, because the threat of this explosion isn't just, theoretical math on a chalkboard. In late 2019 and early 2020, the global astronomy community went into an absolute panic.
They really did. It was wild.
Yeah. Betelgeuse suddenly dropped to 36% of its normal brightness. It was the faintest it had been in over a century. I mean, you could look up with your bare eyes and see that Orion looked wrong. His right shoulder was just fading away. Did scientists think the explosion was starting right then?
There was definitely a moment of holding our collective breath. Astronomers were watching something entirely unprecedented.
Yeah.
But observation logs from NASA and subsequent studies revealed that Betelgeuse didn't explode. It essentially coughed.
Coughed.
Yeah. Because those outer layers are so loosely bound by gravity, a massive convection cell, basically a bubble of superheated gas rising from the interior, breached the surface. The star blasted a cloud of gas and dust out into space that was equivalent to several times the mass of our moon.
Ejecting multiple moons worth of material in a fraction of stellar time. I mean, that is a violent, unimaginable convulsion.
Exactly. Dr. Andre Dupree from the Harvard-Smithsonian Center for Astrophysics noted just how shocking this was. As that massive cloud of stellar material moved away from the star, it expanded and it cooled into a thick dust. And that dust acted like a massive physical veil. It temporarily blocked the star's light from reaching our telescopes on Earth. So the star hadn't started its final explosion, it had just obscured itself behind its own debris.
Okay, but even though the brightness eventually recovered as the dust cleared, the research shows that this event caused a massive paradigm shift in how astronomers view the timeline of Betelgeuse, right? The star didn't just go back to normal, the internal rhythm was fundamentally broken.
That's the key takeaway. For decades, we had tracked Betelgeuse's very predictable pulsation cycles. It expands and contracts, brightens and dims, almost like a cosmic heartbeat.
Right.
But after the Great Dimming, those cycles were shattered. The heartbeat skipped and then resumed with a severe chaotic arrhythmia. And analyzing that broken rhythm led to some really startling conclusions.
Like the 2023 study by Dr. Hideyuki Sayo from Tohoku University.
Yes. They looked at these disrupted pulsation patterns and proposed that the star's core might be much further along in its death spiral than we previously thought. They suggested Betelgeuse might already be in its carbon-burning phase.
I was looking at that study, and what terrified me was the concept of the fusion timeline accelerating. If I understand the physics correctly, a star burns hydrogen for millions of years.
Correct.
And then when that runs out, it switches to helium, which burns much faster, maybe for a few 100,000 years. But once it gets down to carbon, the star's practically running on fumes, right? The fusion process goes into overdrive.
It does. The efficiency drops catastrophically. Burning heavier elements yields progressively less energy to hold the star up against gravity. So the core has to burn them faster and hotter just to survive.
Wow.
The carbon burning phase doesn't last for millions of years. It lasts for maybe a few centuries. After carbon, the star burns neon for a few years, oxygen for a few months, and silicon for a matter of days. Days. If Betelgeuse is actively burning carbon, the timeline for its death has shifted dramatically from a conservative estimate of 100,000 years to possibly centuries, or even decades.
That is unsettling.
And furthermore, 2024 data from the James Webb Space Telescope shows massive, churning superheated gas cells in the star's atmosphere, which suggests a deeply unstable interior that is struggling to maintain its structure.
So what does this all mean? If this timeline has accelerated to the point where you or I or our children might actually see this happen, we need to know the mechanics. Walk us through the step-by-step physical breakdown of the star. How does it actually die, and what will that visual spectacle look like from our backyards?
Okay, the mechanical death of a massive star all comes down to the element iron. As we discussed, the core fuses heavier and heavier elements to fight off gravity. But the fusion chain stops at iron. Iron is essentially stellar ash.
Ash, meaning it doesn't burn.
Right. Fusing iron doesn't release energy, it actually absorbs energy. So the moment the star's core converts to iron, the nuclear fusion engine that has been holding up the star for 8 million years simply shuts off.
The outward pressure drops to zero, just like that.
In less than 1 second.
Less than a second.
Less than a second. The iron core reaches a critical mass limit, known as the Chandrasekhar limit. Without the outward pressure of fusion, gravity wins instantly. The core, which has the mass of roughly 1.5 of our suns, collapses in on itself. It shrinks from the size of the Earth to a sphere the size of a city, roughly 20 kilometers across.
The density is incomprehensible.
It becomes so extreme that electrons and protons are crushed together to form neutrons.
Okay, I love the analogy I read for what happens next. The tennis ball on a basketball effect. If you hold a tennis ball on top of a basketball and drop them both at the same time, the basketball hits the ground, which represents that hyperdense core, and it transfers all of its kinetic energy upward into the tennis ball. And wait a minute, you are describing an incredibly cinematic event, a second moon casting shadows at night. But my self-preservation instinct is kind of screaming right now. You're telling us a blast equivalent to a billion nuclear bombs is happening in our cosmic backyard. Are we absolutely sure we are safe, or is this going to be a sterilization event?
If we connect this to the bigger picture, the inverse square law of light and radiation is our savior here. Let's start with the extinction threat. For a supernova's gamma radiation to completely strip Earth's atmosphere and sterilize the surface, the explosion needs to happen within a kill zone of about 25 to 50 light years.
Okay.
Because Betelgeuse is 700 light years away, it is roughly 14 to 28 times further away than that danger zone. The radiation will diffuse significantly before it reaches us.
Okay, so we aren't going to be vaporized, that's good news. But there is a massive wave of energy coming. We can't emerge completely unscathed from something that bright, can we?
We won't. There are very real, measurable physical effects. The first thing to hit Earth will be the neutrino wash. Neutrinos are these incredibly elusive, nearly massless subatomic particles created during the core collapse. During the peak of the burst, approximately 100 billion of these particles will pass through every single square centimeter of your body every second.
100 billion per square centimeter every second.
Yeah.
How do we survive that? Do they interact with our cells?
You will feel absolutely nothing, really. Neutrinos are famous for rarely interacting with regular matter. They will pass right through the Earth as if it wasn't there. But we have massive underground observatories designed specifically to catch the exceedingly rare collisions.
Oh, like the ones in the ice.
Yes, detectors like IceCube, buried deep in the pristine ice of Antarctica, and Supergiant, which is a massive tank of ultra-pure water deep inside a mountain in Japan. They look for the faint flashes of blue Cherenkov radiation created when a neutrino finally does hit an atom. When Betelgeuse collapses, those detectors are going to light up like fireworks.
God, incredible.
And because neutrinos escape the dying star instantly, traveling at nearly the speed of light, while the visible light is delayed by hours fighting through the star's layers, those neutrino alarms are our only early warning system.
Okay, so the neutrinos just ghost right through us. But what about the actual light and the electromagnetic radiation that follows a few hours later?
That is where the Earth's atmosphere takes a hit. The ultraviolet radiation and X-rays from the supernova will slam into our ionosphere. The physical mechanism here is that high-energy UV light strikes ozone molecules in our stratosphere, breaking them apart. Models suggest we could see a temporary depletion of the ozone layer by up to 5% globally.
Everywhere.
Well, this effect will be specifically concentrated on the hemisphere Earth that happens to be facing Betelgeuse when the light first arrives.
Okay, so a 5% ozone depletion means more of our sun's harmful UV radiation makes it down to the surface.
Precisely. It is not an apocalyptic amount, but a sustained 5% reduction over months is enough to meaningfully affect certain agricultural crops. Even more concerning, elevated UV radiation penetrates the upper layers of the ocean. This can damage phytoplankton, the microscopic organisms that form the absolute base of our global marine food chain.
And we are incredibly reliant on that food chain for human survival. I also noticed the source materials bring up a major concern regarding our modern technology. We rely heavily on orbital infrastructure that wasn't around during the last naked-eye supernova in 1987.
That's a huge point. The initial gamma and X-ray burst acts like an immense electromagnetic pulse. It has the potential to severely disrupt or damage unshielded satellites in Earth's outer orbit, which would affect global communications and navigation. Space agencies actually have contingency plans mapped out for this exact scenario, putting satellites into safe modes.
So it's something we're actively preparing for.
Yes. As the astrophysicist Dr. Brad Tucker noted in the research, a supernova at this distance won't kill humanity, but it will remind us very abruptly that we live in a violent universe and our delicate systems are not immune to its forces.
It is a really sobering reality check, which leads us to the most frustrating, mind-bending part of this entire deep dive. Knowing the mechanics of the explosion and knowing how the radiation and light will physically interact with our planet, we finally arrive at the big question: when?
Ah, yes. The big question.
And the math here is just staggering to think about. Because Betelgeuse is roughly 700 light years away, that means the light hitting your eyes when you look at it tonight actually left the star 700 years ago. The photons you see today left Betelgeuse around the year 1325.
This raises an important question, doesn't it? Because of the absolute speed limit of the universe, the speed of light, we are trapped seeing the star as it was, not as it is right now.
Meaning the core collapse, the massive rebound shockwave, the brilliant explosion, all of it could have already happened.
It is entirely possible that in stellar time, Betelgeuse has already died. The iron core may have collapsed centuries ago. If it did, an invisible wall of neutrinos, followed closely by a blinding wave of photons and gamma radiation, is currently racing across the galaxy toward us at 300,000 kilometers per second.
And there is no alarm clock.
No, there is no cosmic countdown timer we can check.
Aside from a few hours of frantic warnings from the neutrino detectors in Antarctica and Japan, we won't know until the exact moment the light washes over our planet. We're looking at a ghost star, a phantom that might not even be there anymore.
The delay of light turns the sky into a time machine, and we are just waiting for the present moment to catch up with us.
That is just wild to think about. I want to bring this back down to Earth for a moment, to human history, because the sources really emphasize how foundational this single point of light has been to our collective human psyche. For billions of years, Betelgeuse has been a constant. The ancient Egyptians looked up at it and associated it closely with Osiris, the god of death and resurrection, and they actually aligned their grand temples to match its rising in the night sky.
And the deep historical roots continue with medieval Arab astronomers who called it Ibn al-Jawsa, meaning the armpit of the central one, which is where the modern name Betelgeuse actually originates.
Oh, I didn't know that.
Yeah. And navigators relied heavily on its bright, distinct red glow to guide ships across dark, trackless oceans. It has watched over literally every human civilization that has ever existed.
Which brings up an incredibly profound thought I want to leave you with. The documentary script makes this beautiful, unsettling point. Someone will be the last person to ever see Betelgeuse as a star. I want you to imagine the psychological shock to humanity when this happens. What does it do to the collective human psyche when a permanent foundational fixture of our shared sky, something every civilization has mapped, worshipped, and relied on, is violently erased and replaced by a chaotic, glowing scar?
It is a deeply humbling thought. It will be the ultimate undeniable proof to every person on Earth that absolutely nothing in our universe, not even the grand stars we navigate by, is truly permanent. Everything has a lifespan.
Everything is in motion. So tonight, I want you to do something. Step outside. Find the constellation Orion. Look up at his right shoulder and find that reddish-orange point of light. Take a quiet moment to look at it while it is still there, peacefully holding its place in the dark. Because someday soon, that painted ceiling is going to shatter, and the universe is going to remind us exactly what it is capable of. Take a good look while you still can.